Hey guys, so we're going to be on page 96 today. This is section 9.6. Now I know we already had that open book test on chapter 9, but we're still going to do this other section of chapter 9. I just wanted to have the test right after the conversion factor part, just so that would be fresh in your mind. So we're just going to talk about this section now. And this is actually a pretty easy section. It's about energy and how energy is transferred in reactions. So there's two big vocabulary words that you need to know, and they're endothermic and exothermic. Maybe you've heard of those before. There are two different types of reactions. So all reactions are either endothermic or exothermic. So endothermic reactions are reactions that absorb energy. So they take energy to happen, and they absorb the energy from the surroundings. And that energy can be in the form of heat or light or even electricity. Okay, so any kind of energy. And then the opposite of that is exothermic reactions. And those types of reactions are the type that release energy to their surroundings. And again, that can be in the form of heat or light. Okay, you can remember this because En means like in. You can think of enter. So in endothermic reactions, energy enters. And then exothermic sounds kind of like exit, right? So in exothermic reactions, energy exits the system. Okay, another word that you want to be aware of is this term called enthalpy. You don't have to worry too much about this. It's not going to come up too much. It's basically a way of accounting for energy in reactions. The main thing that you need to know about it, actually two main things, we use the letter H to stand for enthalpy, and there's a symbolic way of showing whether a reaction is endothermic or exothermic using enthalpy. So if you see this symbol, a negative and then a triangle H, that triangle is actually the Greek letter delta, and delta means change in. You might know that from one of your other classes. So if the change in enthalpy is negative, that means energy is lost and the reaction is exothermic. If your delta H, your change in enthalpy, is positive, that means the system has gained energy and it's endothermic. So all you really need to remember is that if delta H is negative, and when I say delta, again, the delta is the triangle. So if this is negative, your reaction is exothermic. If it's positive, it's endothermic. Okay, the way this would look, if you like saw enthalpy, sometimes they'll have a reaction written out, like this is the decomposition of mercury oxide, and it happens to have a delta H of positive 181.7 kilojoules. So we know this one is endothermic because delta H is positive. Now they might not always write a positive sign. If there's no charge, just assume it's positive. If it's negative, they'll have to write a negative sign. Okay, so there's that stuff. There's one other thing that we need to write down in the notes. And then there's some examples I want to show you. So, okay, there's some graph stuff, and this is very, very important that you know the graph stuff that we're going to draw right now. So we're going to draw two axes. Okay, and on the y-axis, we're going to label it potential energy on both of them. And the x-axis, we're going to give this kind of vague label of reaction progress. This is just kind of like time, the reaction going forward. And this graph hopefully will look a little bit familiar because we've talked about it before. It's going to look like this, oops, on this side. And then we're going to do one that's a little bit opposite of that on this other side. Okay, so right here, this first part of the reaction represents the energy that the reactants have, their potential energy. And then down here, this represents the potential energy of the products. So you'll notice that the energy of the reactants is greater than the energy of the products. So what that means is that the reactants lost some energy. So this reaction is exothermic. That's the most important thing you need to be able to do is look at one of these graphs and label it as either exothermic or endothermic. So if the reactants are higher than the products, it's exothermic. Now on this side, you'll notice the reactants are lower in energy than the products. So we've gained energy. So that means this is endothermic because energy basically entered our system. Pen's running out of ink here. Endothermic. Okay, a couple other parts of these graphs that are good to know. This distance right here, this is the activation energy. Remember from 9.2, that's the energy needed to get the reaction going. So you'll notice this reaction has a way bigger activation energy than the first one. And then this distance right here between the reactants and the products, that's the energy change that happens in the reaction. So in this case, it's how much energy is released. And in this case over here, it's how much energy is absorbed, because this one is endothermic. Okay, so you want to be aware of which one of these graphs is endothermic and exothermic, and then just be aware of what the different parts of them are. So now I wanted to show you a couple examples of things that are endothermic and exothermic. Okay guys, so I'm going to show you some different processes on this PowerPoint presentation, and we're going to talk about whether they're endothermic or exothermic. So first one, I don't know if you guys have heard of this place. Some people call it Hell's Gate or Door to Hell, but it's actually the Darvasa gas crater, and it's in Turkmenistan, really random location. And it was filled with a lot of natural gas, and then in the 70s, some geologists set the gas on fire just to prevent it from escaping into the atmosphere, and it's been burning ever since. So it's just a seems like almost infinite supply of natural gas there. But all of this burning natural gas, is this endothermic or exothermic? So if you're thinking it's exothermic, you're right. Anytime we have a lot of heat and light being released, like in a fire, that's an exothermic process. So all fires, exothermic. Now you might be thinking that a fire takes energy to start. And that's true, and endothermic reactions take energy, but a fire doesn't take energy to keep burning. Like this burns on its own. So it's only endothermic if you have to keep putting energy in. Since we don't have to keep putting energy in, this is exothermic. So a different example is melting chocolate. Now to melt chocolate, you have to keep putting energy in continually. So that means that process is endothermic. So melting anything, endothermic. Okay, fireworks. So here's a cool video of some fireworks at Disneyland. So fireworks, they're releasing a lot of heat and light. So that's gonna be exothermic. Hopefully that's really obvious. Okay. Let's talk about now this next picture. Water condensing and freezing on your windshield. to form frost. So this one's tricky because a lot of people think, well, it's not releasing heat, so it must be endothermic. But it's not endothermic because you don't have to put in energy to form frost, right? So this is actually exothermic. Water turning into a solid is exothermic. Water has more energy than ice. So to turn into ice, water has to lose energy. It has to release that energy, so it's exothermic. You're not going to feel the energy that it's releasing, but it is releasing energy. If that doesn't make sense, think of the opposite process. Think of melting. Going from ice to water, you have to put energy in to make that happen. So it makes sense that the opposite process, going from water to ice, would be exothermic. You'd have to release energy. Okay, so exothermic there. Okay, plants growing. So while we're talking about this, here's a cool video, time-lapse video of a watermelon plant. And it's growing. Do you think this requires energy or releases energy? So it requires energy. So it's endothermic. Plants growing is endothermic. All right. What about if we have a reaction where delta H is negative 64.7? If delta H is negative, it's exothermic, period. That's it. So that's easy. Let's look at water being converted into steam, as is happening in this video of a geyser. Really awesome video. So does that take energy to convert water into steam, or does it release energy? So it takes energy, so it's exothermic. Okay, there's just one or two more to talk about. What about you do a reaction in a test tube and the test tube feels cold? So this one is a little bit weird. You might think that you're not putting energy into it, so you might think that it's exothermic. But actually, the reason that it feels cold when you touch it is because it's sucking energy from your hand. Okay, so that test tube is like the system, your hand is like the surroundings, and if your hand starts to get cold, that means the energy is leaving your hand. If it was exothermic, it would feel hot. If the test tube feels hot, it's exothermic. If it feels cold, it's endothermic. Okay, and then finally, if we talk about gasoline burning in a car engine, that's exothermic. It's releasing energy, making your car run. Okay, so hopefully those examples help you understand the difference between exothermic and endothermic and how those differences apply in your life. And I hope you guys are doing well, and I hope you have a good day.